Lots of screens.
Yeah.
So we have good weather, everything is okay. I just had a serious struggle before with some tech stuff, but Marcus, the magic tech guy is here, and so he helped me out quickly.
Yeah. Yeah.
I
That's
see
always
you are
good.
in
I
the
mean, just
Caribbean. I thought you were
yeah.
in
I
Austria.
mean, pre-order ended last week, so I decided to take a little holiday here to the Caribbean. Yeah.
You need to do a little bit
And
better than that before you go to the
yeah,
Caribbean.
exactly. Yeah. Yeah, we need to sort of, I mean, yeah, I'm in imaginary Caribbean space right now. So
Okay, okay.
yeah.
You deserve that. You deserve that. We are waiting for summer.
Yeah,
Okay.
summer's on its way. So what do
Yeah.
we have in store today, Andy?
Yeah, we decided anyhow that we do live every Thursday, and that's pretty much the first out of a regular show. Next week I will be not around because I will be in holiday, Corsica. Yeah, we go to that island in the middle sea, Mittelmeer.
So you'll
And
just change your background image, or you'll
yeah,
actually be
the
there?
problem is the water temperature probably is not the one which you want for swimming.
Ah, yeah, yeah. It's fresh.
14 degrees, so
Yeah,
I
a
guess
little
it's
bit
hot.
chilly.
But anyhow, it's our first out of a regular, and we want to talk about what's going on. And we decided to do a little bit more about something which we call tech talk. I mean, it should develop. We are not sure where it goes to, but we think it's interesting to talk a little bit on a relatively high level about what kind of tech we are using. In this case, we talk a little bit about our escapements and why we do that and what's behind the silicon thing. And I think we will learn along and try to figure out what the audience wants to hear, and then get deeper and deeper into the interesting things of watchmaking.
Yeah. So before we get into that, let's do a little recap from, I guess, from the Ukraine donations.
Yeah.
We did a forum post yesterday, and we'll jump into that and discuss a little bit there.
Yep.
And then we'll look at some Supersede
Oh,
prototypes, I
I'm
guess.
too fast.
Yeah.
Sorry, I switched too fast here. My slides.
Yeah.
Yeah, I have a
So,
Supersede.
yeah.
We have a Supersede watch case movie from the supplier. It's prototype number 3.5, I would say. And we are getting parts from Tourbillon rolling in since we had to change the manufacturer. So we are showing a little bit about that, and the rest of the whole show. Is that a show? What we are doing? See, I think it's a show, huh?
Maybe it's a show.
I told to
Couple of
my
middle-aged guys
father-in-law,
mumbling along.
it's we are trying to get a TV channel here because with all
Yeah.
that professional OBS, thanks to the OBS guys for that open source software, it's amazing that we can actually do that. Let's get into the things, or should we?
Yeah. Let's jump into the next slide here.
Yeah, I'm thirsty, by the way.
Oh yeah. I got us some beers. Would you like to have one?
Yeah, I thought you nearly forgot that.
Yeah. Here. You know this one? I'll put it right here.
Yeah. I need
Yeah,
one.
here.
I need one of that
Here, just
too.
grab that.
Okay.
Grab that guy.
So, thank you.
There we go.
Yeah,
All right. Cheers, Andy.
I mean, we need to do some advertising. Tegernsee.
Yeah.
I mean, it's meant to be the best beer in the world. Augustina also pretty good, high on the agenda. But that's where I'm born. And this building is where I went to school. So I went to school technically besides a brewery. I don't know if this did anything good to me, but it was fun. So cheers.
Yeah. Anyways, cheers.
Best beer.
All right. So back to business here.
don't drink and drive, huh?
Yeah.
Back to business. Yeah, let's talk about this horrible war, but we need to talk about it, and we support the whole fundraising exercise in order to bring food to the people which need actually the food, and there are a lot of people who need it. People who followed us, they know that we have put together donations up to 40,000 US dollars, Swiss francs, euro, however you want to call it now. And this resulted in 7 tons of food, and we wanted to show how that looks. Actually, we will get more footage on that from Antonio from crowdfarming, who is taking care of that. And yeah, it looks pretty serious. I mean, that's a cooling facility in Madrid, in Spain. They are preparing, they are loading the whole stuff into a very big truck, and then it goes directly to Ukraine. It will not go to Poland, it will go directly into Ukraine, which caused a little delay because Jose Andres, the guy from World Central Kitchen, actually they were bombed in one of their kitchens. So that was, and because of that, our truck could not yet go out and is scheduled for this weekend. So, I mean, that's pretty scary, real world stuff. Huh? You're sending some food to a place where it should be processed and the place got bombed. Yeah. So I have amazing respect from the people at spot at the front lines, and I think it's worth to follow World Central Kitchen and to see what they are doing, and we are proud that we could contribute a small tiny thing to something useful. Yeah.
Yeah, and with the help of everybody else as well that took part. So and yesterday I just put up a forum post. So if you go to shop.horage.com/forum, you can check that out. And we also have the announcement of the winners there too, listed out. We had it in our previous live stream, or one of our previous live streams.
Yeah.
Everybody was very excited to have won. Fortunately, not everybody can win, but it's
you can also buy one.
In it,
yeah, we are selling watches also.
yeah.
You shouldn't forget that. Okay, so that's pretty much the Ukraine thing, and I think we will continue to report on that when hopefully we get some footage from unloading and what's going on at spot. So I'm personally very interested in that. And and you have a very different connection out of a sudden when you know, okay, this is your stuff which you brought there. It's not just a Twitter feed or whatever. It's real. So yeah, hopefully the best would be if we don't need all that and that war would be over. Okay, so we will see how that plays out. Let's go to the next thing, Supersede. New sample video. I mean, there's not much. We have talked extensively in our last stream about things, but we just yesterday, I think, or 2 days ago, we got a new video from our supplier, new parts, and as we said, we want to try how the whole side flank of the case looks without the cutouts. And with the new bezel, everything's lined up, and so on, and a much more crispy feel on the lines and the surfaces, and it became what we suspected becomes true. So it is extraordinary clean and smooth lines, not so noisy. Everybody who has seen it likes it. We of course need to see it in the metal here when it arrives. But I have another video here. Probably I switch to a different view that you can see that better. Is that okay? Yeah, I think that should be okay.
Good.
Wait, let me go to the one before so you can see that.
Yeah, and one of the things that we talked about in the last live stream, or somebody had brought up, which is quite confusing, was they mentioned the blocks on the side of the bezel.
Yeah.
Lining with the seconds
indication.
Yeah. And we didn't understand what it was meant in the conversation live, but now we do understand.
The cutouts with actually the etching, Now that lines up, and you were, of course, the crowd is more intelligent than us. We too dumb. Where's my GIF? We two dumb guys actually didn't see that. Although our big boss already knew it, of course, and we were then gemaßregelt, or how do you call that in German? I don't know. So I don't know. We talk a lot. But sometimes we are probably too dumb to see what others see.
And as Hans and Franz there, we're probably relatively to the same intelligence level sometimes. So, bear with us. So the bezel is sorted out. It's super well etched. I mean,
Yeah.
the way it's finished when you look at
Yeah,
the
that's now we are. I
numerals
mean,
in there.
as I always say, you need to build something 3 times until you get somewhere. And we are probably doing it 3 or 4 or 5 times. And that's the rule in the mechanical world and also in software. You have to build it 3 times in a certain quantity. You need some time in order to get to a certain quality level. You can't change that fact. If you do it in the first time perfect, it's just luck. Especially when all these details come into play. But let's have a quick look at those 2 movies which we got sent. Shot with an iPhone. It's not a beauty contest here, yeah, okay. So please forgive us if this is not as crazy, prepared, polished video, but I think we can see very well, especially on this crown protector side, that this is a very, very clean thing now. That's how it should be. Crisp edges, clean surfaces, clear dividers. That's how we want to have a case. And here is another one. I can play both, by the way. Huh?
Yeah. The other one is showing.
We can do the
bezel.
overkill here.
Yeah.
Do you hear that bezel? I don't know if you can be heard. I mean,
there is volume on it where you can hear the bezel, but
Yeah,
I'm not sure if it's coming through the feeder.
Bezel click sounds already very good, so it looks also from the video perfectly well. So I think we are on a very good direction here, and I'm very happy with these next. We just need to wait when they come, and then we switch on the camera again, and everybody can have a look at it. Okay, so that's pretty much on. I think we are good with Supersede so far. So next, or do you have any question? No.
No, I think that's it. I mean, the next stage is.
Any questions on the YouTube?
No, not yet.
Okay.
We got some people watching, but actually they could hear the bezel rotation.
Thank you.
Just said that they could hear it, so thank you.
Feedback always appreciated, by the way.
Yeah,
So
it's always great.
Ask stuff if you want to see know some other stuff. That's why we do it live, to instantly be able to respond.
Yeah. So the next stage for these prototypes is that we're going to be building up 20 prototypes. So multiple different colors, different bracelets, and everything else, and those will actually be submitted out to media. So they'll be able to actually be able to look at it, because until now nobody's been able to have a look. And we'll also be able to update all of our photography. So we'll be able to shoot that as it is meant to be and get it up on the website and replace those renders that we've had as placeholders with real images. So that everybody has a much more real representation of what the watch will look like.
Yeah. Yeah, and then we have tourbillon parts, our pain point manufacturing.
But it's solved. It's being solved.
It's solved.
It's solved.
I'm very happy. So we are really making great progress, especially also for our future. I mean, catching up on something is always pain in the ass. Yeah, having to catch up on some supplier bottleneck issue, but we are doing good, and we have invested a lot of time into working together with another supplier in order to also set it up for the future. I mean, it was not just a quick shot exercise. These are actually the parts which we just today. Lorenz was measuring everything, make sure that things are correct, and then others are already cut out and have the diamond cut already is going now to the laser finish. So and you see on that machine, that's machined on a GF machine, which is a local machine maker, and it's a 5-axis machine, pretty serious equipment. So we do the whole thing in one shot, and we do not have we have less problems finding the 0 point when you turn around the whole part. Shall I show also some real parts here? Yeah, we just set up the camera before, and the guys are doing a very good job overall about everything. I'm very happy about everybody. Wait, let me switch the camera here.
I'm very happy that we had this bottleneck sorted out and that we can really start to move at the pace that we always wanted to.
Yeah.
In production, and this will relieve us for all of our production
So that's, for example,
developments in the future.
Pile of that. So you see just a couple of them on both sides. So the next step will be floor plan finish, so magnetic polishing, and then we do the diamond cut. So it's going back on the machine. It must be perfectly positioned on the machine to do the diamond cutting on the edges, and then we cut it out, and then we do the laser and finally the brush, and then go to the coating company and do the plating. Yeah. Here is these, and there's another one here. Some more stuff here.
But although there's multiple processes, those processes all go pretty quick after the initial milling is done, yeah?
Yeah. So you see now the diamond, the diamantage, yeah? Beveled angles. Yeah, and now the last step now, which we do, is the brush. We do it here on our bench, and then it goes to the plating company, and we get it back and then set the rest. So we have a lot of parts here. More. You see trays full of them.
Yeah.
Not very sharp. Sorry, don't have autofocus here right now, but I think
we'll fix that next time I'm back.
Yeah. We are very happy with what's going on right now when it comes to our supply side of things. And
so we had Andy.
There's a question, or?
Yeah, it was just based on Supersede, because I thought we were pretty much wrapped up there on Tourbillon.
Okay. Then Supersede?
Liam was just asking, is it possible to coat the edge parts of the bezel with another color as opposed to silver or just steel?
Wait. The edge parts.
Yeah, the edge part of the bezel.
The edge, the downside parts. Yeah. So filling it up.
This is what I think. Yeah.
Filling it up. Of course, it's possible, but we didn't foresee that for this design. It's a design decision, so we wanted to have it not as hardcore standing out. Probably, I mean, Supersede will have a longer lifetime anyhow. You know, there's always some, how to say, there will be evolutions and variations of the product, and we will see. I mean, everything needs to be developed, everything needs to be verified, and we decided to go for something like this, which is very subtle still. There's a lot going on in the watch, and we didn't want to overload it. There's too much stuff going on.
Yeah, so somebody asked if batch 5 was still on track. As far as all the batches are concerned, we had that batch working framework when we were initially machining in a different way. So we were basically machining in blocks of
30.
I guess 30 at a time.
Yeah.
And now we've actually just done everything all at once. So now it's based on when the time of the order was placed. So if whoever still has to get their watch delivered, it comes down to a time-based order. So if somebody ordered on August 15th and somebody ordered on September 1st, the person who ordered on August 15th will get it before the person on September 1st. So that's just how it's working now. So we're able to move a lot quicker now. As far as the batches are concerned, we just are going to just start working through them all now. And it's all kind of turned into one main
If
batch.
Nothing goes sour, I mean, never forget, things can turn sour at any time. We make everything, and the plating company has a problem,
Yeah, somebody scratches a bridge or something like this.
I mean, we see things happening which shouldn't happen, but they happen, and there's always some sort of risk involved that things can go sour. But I think the most important thing is that we communicate what we are doing, and that's what we are doing here, and people should take part on the journey and see what are the challenges ahead, and we really don't. We are the most happy ones when all of these watches are out the door. I have no real passion for artificial delays or artificial scarcity, you know. That's not my thing. I think when we sell something, we should make everything possible to have decent delivery timelines. That's what people, I guess, expect. That's what I would expect. Yes, we have longer because of the way we do that. We let the people be part of that whole process. Naturally, it takes a certain time, but then it is not just, okay, tomorrow I have a watch. It's the road to that watch is part of the whole exercise. Making people, giving people the chance to understand what we are doing. And then probably that's also important to understand why certain things have a certain price. Yeah? Okay.
Yeah. So, and Liam just had one last question here before we move on to the escapement part of the show. So is the smooth case likely to be the case you will be using going forward? I understand you still need to see it in person first. So yes, we need to see it in person first and to make an assessment and to look how everything's running out, the proportions, the finish, and make a decision from there.
Yeah. Basically, also with these cutouts, there's an extraordinary high risk of losing a lot of parts also. So, and dust collector, dirt collector, you know, there's a lot of, I'm not sure if this was more, or if this is more a typical digital trap, because you can design something doesn't mean you should do it, you know. And that's something at the end of the day, you need to figure that out in the metal and find out how it is. But a watch which has a lot of functions, trying to reduce the noise a little bit is, I think, is something which we should do. Yeah. Just because also sometimes these nice surfaces come out better, and you see that clean side cut, super nice from what I can see of that movie, and I guess from some experience in reality it will even look better. But I mean, it's not our own decision. We try to do that together with everybody involved. So I need to do my camera a little bit here. Oh.
Yeah. So are we on to the escapement portion?
Yeah.
Yeah, so that was the catch up. So if anybody has any comments or wants to ask any more questions about Supersede or Tourbillon throughout the show, just be sure to put it in the chat. But we're going to dive into the escapement portion of this. And this is something that Andy's been wanting to talk about for quite a while, because this is quite a differentiator that we have from others in the watch industry, because there are very, very few. I don't know, Andy, how many are developing their own escapement systems?
It depends on how deep you want to understand the manufacturing behind it and really the geometry. I mean, you can do some developments which are non-functional. On the non-functional side, just change the fork or the wheel look a little bit. But if you really go into the theory of the whole thing, then that's a very different tough thing, and there are not so many who really edge out the small final performance advantages which you can get from modern technologies like silicon, for example. So I personally think so we call this a first out of future tech talks. We also do that in order to figure out what kind of content is interesting and understandable for everybody, and where do we probably get too deep, or where should we get deeper, and where do we need to pull in an expert like Jonas, Pascal, or anybody who is involved into the technical side. I'm not an engineer, but I like to read patterns a lot, so I read that stuff from an amateur standpoint of view. That's my job, I try to dig out new technologies and see if our people can use that. That's my job, so I have a little understanding, but I wouldn't say that I'm a very good engineer or a very good mathematician, not at all. But I think I understand enough to be able to explain what we are doing here. So let's.
I would say you have a pretty good understanding, Andy.
Yeah, I do
a
my
hobby,
best.
Hobby engineer and a hobby
kind of. I rather say probably I'm engineering controller. Yeah? I try to help make decisions because I look at it from a different perspective. I look at it from a intellectual property perspective and from a sort of business perspective. Sounds stupid, but I mean, in engineering, decisions have consequences, and they can have dramatic consequences either for the entire success of a company or for its failure. And so it is not easy for a team of engineers to make decisions, and sometimes it's helpful if someone helps to say, yeah, do it like that. According to my best understanding, that's the best way of doing it. Do it. Don't worry. And that's what I mainly do, I think, yeah. Okay, so let's get into this a little bit more. I need a couple of slides and I have some real parts here. What is the difference, first of all, between what we are doing and what is traditional? On the left side, you see, I just copied that out from the Rolex press release, the Horage Escapement, of course, one of the best traditional escapements developed in recent times, I would say. You see there's a rubies in a traditional fork, and there's a escapement wheel, and then you see ours on the right side, yeah, and they do the same thing, but they cannot be more different at the end of the day when you compare it, and you see that already. Yeah, I think this one is basically made of nickel. Our others are made of steel components and mixtures, and here we are talking about silicon in its pure form as it is used in semiconductor industry. And I will show that even if we do a lot of engineering, that not everything we do is also invented by us, because the whole, let's say, the whole escapement topic is a very old topic. Yeah, it started somewhere 1750 with Thomas Mutch, who actually invented the today, or in the aftermath, where the Swiss lever escapement emerged from the traditional lever escapement. So why do we think that it's the future of watchmaking? And if we call it in our case performance watchmaking, basically the most important part, I would say, is we have much less weight. So this means translates instantly into less power needed to move something, because you need to move that back and forth. We will see that in a little movie. And this back and forth, I always call it, I give this example, when you do gardening and you have, how do you call it, water can, the way you flower the waters?
Yeah.
Water can.
Water can.
So when this is empty and you move it back and forth, it's relatively easy. But if you have 10 liters of water in there, you need a lot of power in order to move that water can back and forth. So, and the same is with an escapement. You need to move things back and forth in order to release the energy step by step, and then indicate the time based on that. Yeah? And the less weight you need to move, the more efficient it is, the less torque you have, the more runtime you will generate out of the same type of available form factor for a mainspring. Yeah?
And just for like a matter of comparison, I mean, how much more efficient can escapement be out of silicone compared to?
Of course, it depends on to whom you compare it, but we are somewhere between 35 and 40%. Mm-hmm. And we see that.
Yeah, go ahead, Andy.
No, probably just ask.
And I wasn't with the company when it was first started.
Okay.
Horage started in 2008, mm-hmm. And as far as at that time, when we first started developing K1, was it the decision made then to start working with silicone, or was there a different escapement strategy at that time?
We didn't want to. We didn't want to do that heavy lifting by ourselves. But because of the nature of the industry and everybody knows that there's a couple of big companies or one big company, and we didn't have access to this existing components because we didn't have a history in the industry. And so pretty much the entire industry at this time was supplied by one company. It was called Nivarox. And we didn't have a history in buying stuff because our brand was technically not existent. So it was difficult to get anything at this time. Today this has changed again. But at this time it was virtually not possible. So we were using another escapement, traditional MHVG. But I was looking into the whole silicon technology already just because of curiousness, and I saw, okay, probably if we do not look into that early, we might end up with an inferior product, a product which is not as good. I mean, you need to think 10 years ahead, when you do something now, the effects are in 10 years. So I said, yeah, we need to look into that whole silicon stuff. And then when reading all these things and looking at what the market is doing and where it came from Bosch, from Germany, and I said, yeah, we probably need to learn about that. And we started to learn how to deal with that. And along the way, we actually learned how to develop around that. And that took a long time. So I probably jump into that slide right away.
So Bosch started it in the early 90s, is that correct?
Yeah, probably let's finish that slide first. So basically these 3 points which are from technical perspective relevant is, so you have less weight, then it's non-magnetic because silicon is a semiconductor. You can't put a magnet there. And what is very important, you have geometric freedom. So you can actually, instead of grinding a ruby flat section, you can actually form surfaces which are beneficiary to better efficiency because they glide in a better way and these kind of things. And
more exacting, right?
Yes. And what is also important is, as I said, it's not so easy to shop escapement parts just at every corner, after the quartz crisis, that there is existing manufacturing technology. The watch industry did not invent that technology. It was invented by Bosch. It's called the dry etching process. It's a brush process at the end of the day. And this available manufacturing capacity, which is non-industry, non-Swiss watch industry or German watch industry, it is used in the semiconductor industry. So it is more easy with a relatively digestible investment to get into that. But you need to understand the math behind it, and that's the hard part, of course, because you can read a lot of books, but at the end of the day, you need to try a lot and figure out if what you're doing it really works.
So Andy, we had one question that came up that might be relevant to the last slide, because you have the 3 points there. Somebody asked, is silicon escapement less sturdy? Does it break easily, or is it more robust because it is lighter?
It is, let's say, robust enough in order to be useful for watchmaking. It has more compression. It has less good compression strength. So when you compress it, that's what it doesn't like so much. But it has very good tensile strength. So when you pull it, it's very stable. This means you need to design in a totally different way as if you would do nickel or steel or something like this. And you see this in our design, and we learned this from actually the professionals dealing with silicon all the time. But it is for what a watch component should do. It is a very, very good material, I have to say. Potentially, personally, and that probably people don't like to hear that, I would say plastic in this component would be even the better material, and I will show some parts later, because long time ago, actually, the predecessors of the silicon escapement stuff was actually rooted in the rise of the microplastic injection molding world. That's roughly at the 60s, 70s, yeah. And it can break, of course, more easy than a steel. But we had so few problems. If you do a correct layout, if you lay out the parts in the right way, then you do not need to worry about that. Is that okay?
Oh, that's good. Yeah, I mean, and it's also, I mean, the escapement is very well protected within
everything's inside
that area, so you're not worried about existing forces acting upon it.
I think the impact you would have to put on that watch, everything else would be broken in order to just break off something which is correctly laid out like this.
Okay.
That's me actually in the facility where we do that. That's in Germany. That's actually the front. You know, in the front you have these two holes. There you put the wafer in there, and then with a plasma and a couple of gases, you actually etch out by using radicals grooves. And you do that, you know, you see that these grooves are round on the side. So you're alternating a process, passivation, etching, passivation, etching. And then you get these grooves, and they can go very deep. And of course, you can make sensors for a phone or for any kind of device. But you can also make components like in a watch. And that was this process, the Bosch process, and the use of the radicals at the end of the day in these gases which you create in this plasma, revolutionized the entire tech industry at the end of the day. With all these sensors, so it is the kind of the basis for the Internet of Things world, if you want it to be, when you say you have a lot of sensors and they talk to the internet, but at the end of the day there's a sensor somewhere, you know, in your phone. Why can you track your sporting activities? Because there's a spring inside, and very likely that spring was formed from a dry etching process, namely from a Bosch process. And to do that at scale, this was the big achievement in 1992, I think. It was 1992 when they filed that patent. So, and that what you see in the rear here, that's actually the back of these two holes. So there is a huge equipment exercise in the backside of the clean room. And these are the plasma reactors in which you create this plasma, where then the gases alternating create actually these etching processes. And you have these different radicals, which like to react, and you actually shoot with ions on the material, if you want to say it like that. And that's it is the best research process in the world, industrial process. So, and the institute we are working with, they have production capacity. They work a lot for bigger companies, also in Germany, in the car industry and in the semiconductor industry. And they were the second company in the world who had this type of plasma and Bosch process capability. So besides Bosch itself. And this means they have a very vast amount of data which they can look at, and this means they could help us to tune actually the etching process, because you know, you have gas, you have pressure, you have flow, you have all kind of things. Even the way you make the parts on a wafer is very important to consider, because the gas is, you know, it flows somewhere, it needs to flow in the right way, otherwise you have tolerances and you want to reduce that. So I can show probably a wafer here if we want to do that.
Yeah, because I mean, that was, you know, one of the questions that I had for you as well, is just to show how those things are etched out, how they're cut out, how does this flat piece of silicone become, you know, parts within an escapement.
So let me switch my thing here. So that is actually the view on a wafer. You see the camera? So you see that's a wafer, relatively small wafer, but we would change to bigger sized wafers in the next year. But for our, sorry, Jonas calling. He should know that I'm live, huh?
Yeah.
Totally
Airplane
forgot.
Mode. Yeah.
So, and when we go deeper into that, Well, there's still a lot of space, so we have a lot of room for optimizing the space use. We were very much on the conservative side when we do it like this. And these are actually, and they are held in place with some very small holders, and then we break them out. And that's how and afterwards we marry them with the axle, and then they get put into place, yeah. Probably a different camera shot.
So Liam has a question in here, but we'll get to that one later on because I had the same question as well because it keeps coming up. Yeah, anybody else has any questions in the chat, be sure to hop in and ask away.
You see the color now in the better way. Some of them are broken out already, yeah, from a shock or something like this.
One of the questions that came up in the past is we had a customer one time asking for a specific color of silicone because there's different companies that produce. There's a few, but they all seem to have a different color.
That depends on the way.
Behind that?
That usually depends on some certain after treatments. Basically, I probably could go into the next slide. When you hear silicon, it is silicon in its raw form usually, because otherwise you can't really etch that correctly. And usually, I mean, silicon is kind of a crystal and it has different planes. Yeah. You don't see my. Sorry. I need to switch over to that. Is it too small? I think we do that. So, crystalline structure. There's a diamond unit cell, and then these silicon atoms are organized in a certain way, and dependent from which direction you actually look at it, you have different planes. And these planes, you call it 100, 110, 111, these are the three main planes you actually can treat. And depending on which plane you use, you actually need to use different etching process. But at the end of the day, it's this silicon in its pure form. And that's also the advantage of silicon. You can have it in a very high purity. And that's why that process works. So you can do etching with glasses also, but you will not get a vertical side flank. You will get actually an angle, and that's a problem. For example, glasses are same etched in a plasma like a silicon, and then they're bonded together to make some light emitting diodes, yeah? For example. But that's basically silicon, and what people do in the after treatment, or for example, the raw surface on the one side looks different than the etched surface on the other side, this will reflect light in a different way, obviously. And depending on even how people shoot it, some companies use diamond coating on silicon. We also played around with that, but decided not to go for it because it adds extra cost, and this creates a little bit more of a brownish look. But that's basically more because the light reflections are involved. Yeah.
Yeah. So
sorry, nobody saw me here.
Yeah.
You need to tell me when I have to switch.
Yeah, sorry about that. All right.
So that's already pretty deep stuff, you know. I mean,
yeah, it's getting really deep into
this means you really need to understand etching in itself and all the processes of passivation, silicon oxide, and what you masking and photolithographic films and all these kind of things, because it's different. There's dry etching and wet etching and many different processes. So, but basically, it is, as I said, it's the best researched process, industrial process in the world. So people know how to do that. It's not a watch industry invention. I have to be very clear on that. We can look at some of the very, very early parts we did. You see that looks already different in its shape. That's on a scanning electron microscope. In German you call RAM, raster electron microscope. And that's pretty small stuff. You know, when you look at these grooves here now, that's the interesting part. That is very small. You know, just to be clear, we are talking about 10 microns on this distance, and such a groove is actually the impact of these ion etching gases on that surface. And you see it in 2 stages, yeah, because we actually have a 2-stage etching process. We did this, I think these parts were used after, were shot after 2 years of using. So you don't see any wear on these parts. And that's fascinating, yeah.
Yeah, so speaking of wear, I mean, Liam just had to leave, but his question, and I wanted to bring it up as we came to this, was, you know, there's this myth that silicone doesn't need oil or lubrication, yeah. He's asking specifically that does having silicone mean you don't need to oil lubricate the impulse
You have
phase?
to. You have to. You have to. You know, 2 things rub each other, there must be something in between. If something is self-lubricating, then there is some sort of lubrication in the part itself, like fluor or whatever, PTFE, dry lube. But silicone doesn't have a self-lubricating kind of. At the end of the day, it's glass, you know. And something must be in between, because when you look at the amount of impacts over the lifetime of such a product, which we can look at it later, it will become evident that there must be some lubrication. It's the same like the coaxial, where people believe that it doesn't have to be lubricated. That's not true. There is lubrication. George Daniels just washed the parts in benzene, you know, in fuel. and that's obviously some very small lubrication involved. I mean, there will be a lot of research going into dry lubrication of silicon. We see that in the MEMS industry already, but that's a very tricky area, and it comes with the increased use of sensors and the more accuracy you want to have out of sensors, which are also moving, or highly sophisticated stuff which is rubbing each other. And there we will see new especially in the self-lubricating area, we will see things. But at the end of the day, we decided to put very few, but a drop of oil is needed. And that turned out to be the right thing to do.
And because of that, it also has a much longer service interval, yeah? Or interval between services, it can.
In general, I mean, you have less stress on the parts, you have less torque because of the less weight, you have increased a better gliding efficiency. I mean, shall we show that little video?
Yeah, that'd be great.
Wait, let me dig that out. Was Escapements. So exit and entry. Wait, I need to. It's pretty fascinating. Wait, how do I get that thing over there?
We're watching the video now. It's up there. Yeah.
No, you don't watch it. Now we can watch it. Yeah, that's actually a shot on our escapement. Ausgang means exit, means when actually the wheel is released from the balance wheel. It makes a turn and it releases actually the anchor from the axle wheel. That's 4,500 frames per second high-speed camera shot. And you see, do that several times now, you see now it disengages and then it's gliding, and actually it is pushed from that impulse in order to keep actually the balance wheel spinning. And we have another one. It's super fascinating.
How tight are the tolerances in between there? It's amazing.
It's nothing. The point is, the tighter the tolerance you make, let's say, the more precise and accurate, or the more efficient the whole efficiency output is. But at the end of the day, you need to find a trade-off. I mean, these parts are actually sitting in a bearing and they are moving, you know, there's play. So you need to find the right trade-off, just enough tolerance in order to not be affected by the other tolerances which are anyhow there, and not too many so that you don't lose the efficiency or have some other problems on the way. So that's pretty cool stuff. if you think about, and that is all very small, you know. And the funny thing is that happens many times per year.
25,200.
25,000
per
per hour. So I made a couple of numbers because I like those numbers. Just some facts here. Wait. Well, shit. Sorry.
Yeah, no problem. So somebody was just asking what would be the service interval of the Supersede and the costs. We always say service it only when it needs it. Yeah. And so maybe 5-10 years, you know, somewhere in there. And cost, we have it listed on our site. I believe we're at $450 for a K2 service. So it's just under customer service on our website. We can go and look at all the servicing details there.
Yeah, getting back to what that in numbers means. Yeah, our watch runs at 25,200, 3.5 hertz. That means 25,200 beats per hour. When you take that, when you say, okay, one teeth, the pellet of the anchor, call it this one side of the anchor, engages with a wheel 12,600 times per hour. Just the thing which you saw, you know, that gliding of releasing action. So that happens 12,600 times per hour. It happens actually 302,000 times per day and 110 million times per year. So then you take it by times 10, you get a feeling how much actually stress is put on this part. On the wheel, on the wheel is different. You have 20 teeth on the wheel. You can see that. Obviously, it's 1/20th of the stress, or 1/10th, if you say it like this, of the others. So that's pretty serious. You asked me on the weight, and I asked. Then I asked actually Pascal to give me, because we didn't have a scale to weigh it. It's too small here. We would have to put a lot of them together, and then that doesn't make sense, but the cut is pretty accurate. You can roughly say such an anchor as our design made in silicon weighs 0.0017 grams. And that is 36% of the weight of a regular one, or in other words, is 2.8 times lighter than a traditional one. So that makes this, in combination with an improved geometry, makes it pretty clear that a traditional escapement will have a hard time to get to the level where we are with this technology and with this geometry. Yeah. So
yeah, thanks for getting those numbers.
Yeah,
I was always interested.
That's the type of math I can do. That's the type of math I can do.
You ask somebody else to do it for you.
Yeah, I think it's time for a beer.
Yeah, it's time for
Cheers.
So
Dumb and Dumber, yeah.
Yeah, Dumb and Dumber here at the computer, giving an escapement tutorial. But no, Andy, you really do. You've invested a lot of time and work into this, and it's
and we
pretty
do that
incredible.
since 12 years.
Yeah.
So we were talking about the timeline. You can come in. Yeah, someone coming in here. My nephew, he wants to see how we do that. So yeah. I'm just live. Just don't say anything. But you can see. Yeah? 12 years ago, we kind of did it the first time, and we started with not much know-how, I would say. And you can. Yeah. So we started with not so much know-how, and it was very, you see that already from the level of sophistication we have reached until we come here. That's what we do today, and this was a long way of optimizing, learning actually how we design for correct etching procedures. Because you have to imagine, for example, the top of the wafer and the bottom of a wafer will come out different, dependent on how much space you leave in a groove. How do you design actually a hole? It will have an impact, and you want to have a very vertical structure. So we needed to learn that, and I think these designs today are really optimized for etching them in a perfect way. Then, yeah, how do you assemble an axle into something like this? That is not easy because I said before, the compression strength is very bad. So what do traditional watchmaking loves to do? Rivet stuff together. So riveting comes with pressure, and that's what silicon doesn't like. And so if you rivet stuff, then it will kind of explode because you put pressure in these parts, and that's perhaps the reason why so many other companies had some sort of problem, and there was the myth that stuff breaks. Yeah, if you don't design it in the right way and don't respect actually the nature of silicon, and you put pressure on the interface between the silicon part and the axle, then you don't need to wonder when there's another impact somewhere that this stress adds to the other stress, and then probably it breaks. So I don't wonder about this. We do not really know that problem, to be honest. Very few broken components in the past. And then, as you saw on that video before, our edges in the front are not completely straight. You know, you actually have an impulse plane distributed over the teeth and the anchor. That's in one part of the Swiss leather escapement. English ones have only just the teeth is one point, and then there was another escapement type. So, and you need to do the engineering to find out the best way of doing it. But the geometry which you can create by this type of manufacturing process, namely making a surface in a certain shape in the critical area of the tip and the tooth, yeah, that's what you cannot do very well with traditional manufacturing techniques, and that's what I wanted to show. So it looks, we are not, you know, I mean, we also borrow know-how from somewhere, and I brought a little very interesting product here. Shall I get into that?
Yeah, well, I wanted to ask you on this slide here before you get into that, is that you have 10 variations that came to light, and I was talking to a customer this morning who had just received his tourbillon, and he was asking about, you know, how movements change over time. And I had relayed that, you know, basically there's each movement goes through different versions, and within those versions we have sub-versions of the development. And with the escapement, we've gone through the same sort of process. Was there any point within this map that you're showing here, Andy, that we made some sort of significant breakthrough that changed sort of the development process of silicon?
Yeah, I think in the beginning, I mean, what did we do in the beginning? We kind of copied the traditional Swiss leather escapement with its pellets, with all, for example, this banking pins which you need. We just copied the tradition. And of course, you don't create major advancements. But then, when we were looking at some very old inventions, namely the Tissot patent, I call it, yeah. This actually, this was in 1965. So in 1965, the people were thinking of, it was just at the beginning of the quartz crisis, how do we actually make those things better perform and cheaper to produce? And then there was plastic injection molding coming around the corner. And and we saw these little grooves, and in order to remove these banking pins, which are usually limiting the movement of the anchor, and we said, oh, why not taking this 1965 invention and incorporate it into our modern made of silicon escapement, and that's where we started to really start to think about, okay, we shouldn't just do what we know right now. We should really try to combine the existing knowledge and design for silicon and what we can get out of it. And this, I would say, after 2 years, 3 years, here out of a sudden, in this area, this probably was 2013. Someone got very nervous in our team because out of a sudden the performance shot through the roof. The runtime was out of a sudden super long because we invested more math into it. Yeah, and we found out the mainspring had too much torque because the efficiency was so high, and the escapement didn't need all that efficiency, and we needed to bring down the torque. And out of a sudden, the movement was coming from 56 hours power serve to 60 hours, 65 hours, and we are getting close to 70 hours. And this was an ongoing process to fine-tune actually the geometries in the front area, and and figure out what is the best mechanical design to really utilize this to its maximum level.
Okay, so what is this this product that you wanted to show, Andy?
Yeah, I wanted to show some cool stuff here.
Okay.
Not only slides, not only slides.
Yeah. Can I ask one thing before we go to that product though? I know what it is, but many people might not know what it is. But the slit that's inside of the anchor,
okay. Yeah,
cutouts, and also inside of the escape wheel.
I have been here.
Yeah.
So that slotted thing here.
Yeah. Those.
This is actually that's something where we applied a patent for. This is something in order to hold we cannot rivet the axle into that part, so we need to glue it together. Gluing needs curing. Curing time, during the time of curing, you actually could disalign something. And we do not want to make a perfectly have to make a perfectly precise hole into these components. So we want to have a certain flexibility, and these actually beams, are they beams? Yeah. They just apply a certain pressing force on two very well precisely defined spots, so that stuff is 100% centered, and it's super important on the balance on the escapement components that they are perfectly centered. With the spring, main spring, hairspring, it's not so important, but there it's super important. So these beams are there to position the part during gluing and keeping them in place. Then the glue also has more bonding surface, so it's more secure because the glue actually gets around these free areas here, which you see there, and you completely have a completely stress-free part. Whereas if you would make a hole, then you would have to make, so the turning part comes off the machine probably plus minus 0.002 of a millimeter. Then you have this wafer, and all these parts on the wafer, they have different dimensions. If you believe it or not, parts outside are a little bit different than parts inside and on the middle, because the gas is flowing over that wafer, the iron, the etching is going down, and there is tolerance. So they look the same, but effectively they're not always the same. So you have tolerances, and you do not want to be forced to make a precise hole in a part where you have tolerances all over the place. So in this way we can control the two spots where the axle needs to be aligned to. That's something which we can control to the micron level, and the rest we have relatively open, and we leave it to these beams in order to do the job and put the axle into the right place. And during gluing and after gluing, then it's fixed and in the right place.
And what else is unique? We're doing all that gluing and assembly directly at Horage.
We developed the gluing process by ourselves. So that is real know-how, I would say. How do you design for mass producible components like that? Because the etching process is a mass production process. It's a batch wafer. It's not one by one. So a big wafer, you can get probably 1,000 anchors on one wafer. And then, yeah, the problem starts after that. How do you actually fit in those axles in an effective way that you don't have damaged or broken parts, that is stress-free, that they are perfectly centered, that they are perfectly 90 degrees angled? Because all that, if that is out of tolerance, then you have precision tolerance, precision problems in your watch. So I would say we have learned a lot. I mean, it was super interesting to learn all that. And we are, I mean, just to give you an idea, I mean, we throw a lot of parts away. I have a little bit of a high CPU load, to be honest.
Okay. Well, you look to be doing all right there.
Yeah. So there, yeah, scrapping stuff. That's when I show parts, you know, I take them out of a scrap box. This is all stuff which we throw away over time. Nice stuff, but you can't do much with it anymore. Probably look at it like this. That's a brass plate, by the way. So when I get close, you see the light. So the left one, that's the wheel. There's a little dust there. And the left one is actually the regular one.
So the left anchor is the one that's in K1, K2, yeah? Yeah. And the one on the right is tourbillon.
The one on the right is a tourbillon, which is angled because you don't want to have this rear of the fork sticking out into, and you see when I change it a little bit, then you see the blue. So don't be mistaken by some colors you see in some pictures. If it's silicon, then it's silicon, and then it's blue. Bluish.
Yep.
And if they coat it with some sort of stuff, then we don't know, and it can also change the color a little bit. But the material is the same. Effectively, the two have the same function. Yeah. So now I wanted to put the 1965 exercise, you know. There's a watch called System 51 from Swatch Group. Very nice movement. And surprise, surprise, the foundations for this watch. That's
from System 51, this is the foundations, yeah?
That is kind of the foundation. It was at the time where plastic was high in demand. Actually, the former Swatch Group companies played around with plastics. And that's called here, what's the name? Auto Loop, Tissot Auto Loop. A lot of scratches there, but it is an amazing piece of engineering. I mean, if you think about that, you know, it's not running, and I just give it some spins, you know. Different. So now, and it starts. Cool, eh?
When was its last service, Andy?
Never. I don't know. I bought it somewhere in eBay because I wanted to have that thing, and there it is. And it's doing pretty much the same thing than ours. And of course, it was produced for maximum low-cost, mass-produced thing. But basically, for example, that there are no banking pins, which you can see, is what we are, where we lend a lot of ideas from, and we incorporated this into a silicon type of material. And at the end of the day, they have both advantages, namely geometric freedom to a certain degree, very low weight, plastics. Some people add the term high-tech plastic, has obviously a self-lubricating effect. Everybody knows this. When you touch a plastic bottle, it is different than when you touch a glass bottle. Yeah? So, and today, I think the Swatch Group is using a certain amount of plastic escapements in a couple of movements. And from technical standpoint, I would say that's a good idea. Yeah, it's probably from marketing point of view, same like in the bike business. You know, nobody wants plastic. on a derailleur.
They want carbon.
That's the worst stuff. But plastic, sometimes makes sense. But people like aluminum, yeah, and it's not always technically reasonable to do some sort of things. It doesn't help when you can't sell it, when people don't want to have it. Then you obviously need to change your strategy. But that's a pretty cool thing, Auto Loop from Tissot. I join here with...
What do you have here?
Yeah, that's ours.
Array. Yeah. An old dusty
thing here.
Prototype here.
It's one of the first prototypes I took out of. I don't have a cloth here. Sorry, forgot that. Yeah. But basically that's what we are looking at. We're looking at things like this. So we are looking at technologies which have their origin many years ago, solutions, and they continuously needed to be improved over time. Yeah? Nothing comes by accident. You need to work on that. It's a little bit too dark here. Does it get brighter? No.
Did you block one? No, there you go.
Yeah, I think it's the two different materials don't like each other in front of the camera.
Yeah.
Cool stuff. I like that thing. Auto Loop, Tissot, our idea-giving product, some kind of.
Yeah.
I think the watch was 68 or 70. Patent is from 1965.
So the chat has been relatively quiet. Maybe we went too far down the
too boring
tunnel here. But if anybody has anything they want to ask in the chat,
we are anyhow pretty much done, huh?
Yeah, we're pretty much done. So
we are over. We are 10 minutes over.
Yeah, we're well over our hour. But I mean, what else were you going to do this evening? Probably eat some good food. Yeah.
Yeah. Drink some beer.
Yeah.
Look at some tourbillon components. Yeah. Yeah. No, that was pretty much a little bit of an. You see, I mean, easily a couple of hours can be spent on not going even into any real details in this field. I mean, we just touched the surface,
Yeah, we talked about escape wheels and anchors, but we didn't go into balance wheels, springs, all those type of things. So
and we didn't go into more details, all this kind of history stuff. I didn't want to make a history exercise because a lot of people can write about it and you can buy books. So it was more important to talk about what we do and where our why we do it and where the inspiration and input came from. And and people are welcome to come here and have a look at this. And we hope we can continue to innovate around this area. And it doesn't come easy. It's nothing which goes quickly. I have my different camera here. Sorry.
Which one?
Now.
Oh, yeah. Now you're back. So I guess that's it for today. I mean, we'll come back next week. Andy, you're going to be on holiday. So how are we going to do this when you're on holiday? Huh?
That's the question.
Yeah. If you have Wi-Fi, if Andy has stable enough Wi-Fi, we'll do this.
We can do that out of. We can try to do that out of Corsica.
Yeah.
Why not?
Yeah. At least your background will be real.
Yeah. I have the real sea down there then.
Yeah.
Okay, let's drink the last sip from my beloved Tegernseer beer.
Dude, I'm glad I could get that right through the live stream.
Yeah, it's magic. Beaming.
Mm-hmm.
Isn't that the beamer?
It's the beamer, Silicon Escapements to beaming beers to the internet. We're true innovators here.
Yeah, okay.
So thanks. TC says thanks for taking the time to share these guys. All right, you're welcome. Thank you for joining.
We will do more of that. Then we need to do the typical ending exercise. Leon, our graphical mastermind said we need to sit still and say nothing and then end the broadcast. So I sit still